Yeah, hello, I'm Stefan Brückner from the Friedrich-Alexander University Erlangen. Today I want to present this poster. And first I have to give some context. It's about phase difference-based localization. So typical what you have a receiving aperture with multiple antennas. And there first, typically you get an angle of arrival, which you get first. And then you triangulate this where the beacon, the active beacon that transmits this signal is received. This has multiple drawbacks. Therefore we skip this step of the angle and directly put the phase differences into a Kalman filter. That has multiple advantages, but one large advantage is we can cope with the ambiguities that comes from the sparse antennas array we are using. So we first put various antennas in it that have a very small baseline and therefore are relatively unambitious. And then we put larger spaced antennas in it, and there the accuracy improves. But due to several problems, we cannot build antennas with 0.5 lambda spaced, and therefore we cannot get absolute ambiguity like you would have in this case with 0.5. So that's why we build an antenna structure that comprises of 3 antennas that are spaced in this case 2 lambda and 2.5 lambda. And we get the difference between these 3 antennas, and then you can see they act relatively same than 1.5 lambda, despite not being close together. And with that, we can get it unambiguous and accurate at the same time. We also did this on a practical experiment. So we have our receivers on a ceiling, 3 of it, and a beacon that is moved by a robotic arm in the room. And then we set the starting point on the edge of the room where typically the filter could not find the position. But with this technique I presented, it was able to find this starting point and then track the beacon.